just like that. So that's just taking that piece and just dropping it down with the 2. So everything you're seeing here, right? This, right? This is all coming from that integral right there, right? That's just that. We still have to deal with this, don't we? We still have to figure out what this is. Plus 1/2. How do we find the antiderivative of that? You'll see a basic u sub doesn't work now, right? The basic u sub, because if we let u be this, the derivative that's 2x, and we don't have 2x, right? You cannot put an x over x out here. You're not allowed to, you can only move constants in and out of integrals. You cannot move variables in and out, all right? So we're kind of stuck, yeah? All right, I'm going to put this problem over here. I'm going to bring the 1/2 with me because I'm afraid that I'm going to forget it. So let's start scratch work over here. How are we going to handle this? Oh, hey, that 2, we should pull the 2 out, shouldn't we? We should pull the 2 out so it knocks that 1/2 off. Can I do that? Okay. Let's pull that 2 out. Comes out here, and it's just a 1. So this is what I'm trying to do, right? This is it. I'm gonna clear all this off the board. I'm going to leave that over there, right? Because this is where we are, and we're kind of waiting for our answer over here. I'm going to clear all this out of here. All right? Shit, how do we do this? Any ideas? Okay, so yeah, try maybe expand it out and complete the square. Well, if we expand it, what's going to happen is we're going to get a 4th degree polynomial, right? We're going to get a 4th degree, just like we had before. So completing the square works for, like, our formula 17 and 19 and 20 work for quadratics. It's not going to work for 4th degree polynomials. To the trig sub, that's it. Okay, let's try it. What made you think that? Practice? So you've done enough to kind of see it? That's what it takes. Now look, admittedly, this is just a shot. We're taking a shot at this. I don't know. We don't know what's going to happen here. But do you all agree that's the same thing? Right? And now we're going to try trig sub. We forced it. We were stuck, right? We have to say we were stuck, right? There was nothing we could do. No basic u sub. I don't know. I don't think integration by parts is going to work here either. So the thinking trig sub, well, at least I have something squared plus a number squared, right? Like x squared plus a squared. At least I see that. So think trig sub. Just need the root in there. Okay, force the root to be there. What's the trig sub here? X is a tan theta. So for us, it's just 1 tan theta, right? All right, dx would be secant squared theta d theta. And then the square root of x squared plus 1, I'm not going to show the work, but that would be secant theta. Is that all right that I'm not showing that? All right, let's rewrite the problem, and let's hope for the best. Okay, integral 1 over. Okay, the square root part turns into secant, doesn't it? But it's to the 4th power. So this is secant to the 4th theta times, don't forget the dx, right? The dx is what? Yes. Secant squared, cancel, it's going to become secant squared on the bottom. 1 over secant squared flips and becomes cosine squared. Cosine squared, power reducing formula.
Yes.
Right? All of that is going to happen nice for us here. So this now becomes integral 1 over secant squared theta d theta. And that is just 1 over secant squared is what? Cosine squared theta? D theta. And I said that last class, I promise you that you're going to have a problem where you're going to have that, right? Didn't I promise you that? I feel like I did. You'll have a trig sub problem somewhere on your next test where you're going to have a cosine come out at some point. That way, you can bring out the good old power reducing. Ah, shit, I just erased the other answer. Oh well. 1/2 comes out, integral 1 plus cosine 2 theta d theta. Time for the antiderivative, 1/2. Okay, antiderivative of 1 with respect to theta. Theta plus 1/2 sine 2 theta. And then plus c, right? So that we've done enough times, I hope, right? But I told you last time, right, last class, that the reason I wanted to do this problem and have this happen on the test is because not only do I want you to show me the power reducing formula, I want you to also show me the double angle identity that you need to turn this sine 2 theta into something you can handle. So I'm going to go now to what? I'm going to handle that, but reference triangle. Okay, my reference triangle is based on this right here, right? It's based on that. So I have tangent theta is x, so I'm going to write as x over 1. My reference triangle looks like this. Tangent is opposite over adjacent. That means the hypotenuse is this. And now I can figure out all the different values. So 1/2. Okay, what's theta? Theta, you have to go back either here or here. Take what on both sides? Arctan, right? You take arctan on both sides to get theta. So theta is just arctan x, right? And then, oh wait, I never finished this. Hold on, let me clean this up. This right here became 2 sine theta cosine theta, right? That's a double angle. And this 2.5 go away. So I just need to know what sine theta is and cosine theta is off my triangle. And it'll be plus right here. So sine theta is x over square root of x squared plus 1. And cosine of theta is 1 over the square root of x squared plus 1 plus c. I can put these two together, right? Mm-hmm. Okay. So 1/2 tangent inverse x plus x over, multiplying the bottom together, you get x squared plus 1, all that plus c. Okay, don't forget, this was just, we already had another part, didn't we? There was another part that I erased, right? So earlier, I had the first half of the answer. It was negative 1/2, or 1 over 2 parentheses square x squared plus 1. Yeah, so just throw in front of that negative 1 over 2 x squared plus 1, right? That goes in front of this. Okay, wow. There's a lot going on there, isn't it? What I hope you're seeing, okay, what I really hope you're seeing, you take a step back from everything here, and like, why are we doing Cal 2, right? What I hope you're seeing is the amount of mental organization and, right, isn't this just a different type of thinking? Like, this is not like Cal 1 thinking, right? There's a lot more going on here. It's more abstract. And this is what we're trying, this class is helping develop that part of your thinking as an engineer, computer science, whatever it is, right? This is the aspect of the way you think that needs to become more refined, I guess, right? Like, never in the real world are you ever going to be sitting here doing this integral, ever, right? But there's a big difference between people who can do something like this and people who cannot. And that's when I'm saying, like, I'm not saying overall, like a person in their totality, right? I'm just saying when it comes to analytical thinking, right? There's a big difference between someone who can do this and manage this and somebody who can't. And so
basically, employers are going to look for somebody who can think this way.
absolutely, right? An engineering firm is going to want to hire somebody who's a problem solver, right? Just generally is a problem solver, who gets something difficult and doesn't just kind of be like, well, I was never good at really math, you know? Like they're like, well, shit, I'm not sleeping till this is over, you know? It's a certain way of thinking, and where do you learn that way of thinking? Classes like this, where you have to think that way, right? So I'm just trying to get you to like see the forest through the trees here. I have a student of mine who's working at NASA right now, who took me for Cal 2, and I was talking to him last semester, and it's like, man, I need to get you in and talk to my Cal 2 class. Because if you tell them, it'll mean more than when I tell them, right? Right? Wouldn't it be more? Probably, right? So, all right. Maybe I'll get him in here. Maybe I still will. See if I can reach him. Oh, I don't know, he's working on his PhD. So he's doing like something in NASA while he's working on his PhD. So I don't know all the details. Yeah. It's classified. Well, I do have another student who had me for calculus as well, who was working for NSA. And so he literally could not tell me what he was doing. But all right. We're a little over halfway in the class, time-wise. So now it's time to get into partial fraction decomposition. So the whole goal here, all right, of this section is to be able to integrate rational functions. So the first thing is, what is a rational function? This goes back to college algebra. A rational function is simply the ratio of two polynomial functions. And I gave you a bunch of examples right here. If you look at each of those examples, f, g, h, j, k, every single one of those is a polynomial divided by a polynomial. Polynomial divided by a polynomial. Polynomial divided by a polynomial. But notice none of those look like what we were just doing, right? Like I was very, very specific about constant over linear, constant over irreducible quadratic, right? Linear over quadratic. Like we were looking at very, very specific cases. None of those fall into that category. So can we still find the antiderivatives of those? Yes, but there's going to have to be some sort of attack, some sort of approach, right? Some general approach. So that's what they are. Imagine integral signs in front of each of those. That's where we're headed, all right? So before we get into that, let's just kind of motivate the idea here of what partial fraction decomposition is. Recall from way long time ago, college algebra, that if I put 1 over x plus 1, and I told you to add to that 2 over x minus 3, that in order to add those up, you would have to get a common denominator, right? And so what we would do is we would multiply this fraction by 1. In this case, it would be x minus 3, and then over here we'd have to multiply x plus 1, x plus 1. This all look familiar? Okay, and then we put those together. Let's see, we multiply these two, we get x minus 3. And on the bottom, we get the common denominator. I'll just leave it like this. Then over here, we have to distribute the 2 through to both. So we get 2x plus 2. And then over the common denominator again. And since they both have the same denominator, I can add them. And when we add, right, we just add the numerators up. So x minus 3 plus 2x plus 2. All of this over the common denominator. Let me go ahead and multiply this out now. I'm going to FOIL the common denominator out. It'd be x squared minus 2x minus 3. What's the top? 3x minus 1 over x squared minus 2x minus 3. Right? In college algebra, you learn to do this. I don't know, you probably learned it before, but at some point you had to take two rational expressions and add them or subtract them, right? And put them together, common denominator, right? What we are going to do is we're going to start here and try and get back to the original problem, right? So start from this and get back to this right here. And the process of going from here to here is called partial fraction decomposition. Okay, that's the process. So from here to there is just called adding two fractions together. Okay, partial fraction decomposition is starting with a single rational expression and taking it back to a sum or difference of different unique little fractions. Much harder process, right? Do y'all see what makes this process so difficult? If I just think about what it would take to go just from this step to this step, right? How do you know that 3x came from 2x plus x? There's a lot of different ways you could have 3x, right? It could have been, what, 5x minus 2x? I mean, there's an infinite number of ways you could have got the 3x. Same with the minus 1. So how do you know that minus 1 came from minus 3 plus 2, right? It's impossible, isn't it? So we have to have a method. So here's the method. You ready? There's a formal method that you can read in a book, and it's really complicated because they use all these symbols and things like that. I'm going to try and just break it down very, very easy if I can. Let's see. Let's take this 3x minus 1 over this. The first thing is the denominator factorable? Yes, it factors, right? So the denominator factors. Yes, you have to be able to factor. All right. So it factors, yes? Look at each of those factors. This is what we would call a linear factor, right? That's enough. You get 2. Okay, you get 2. That's it. And this is a linear factor, right? So what you see here are two distinct linear factors. Distinct because they aren't the same factors, right? This isn't x minus 3 times x minus 3, right? This isn't x plus 1 times x plus 1. They are different from one another. So we call these distinct, right? These right here are distinct linear factors. So I'm trying to do partial fraction decomposition on this, right? First step is to factor it. I look at the denominator's factors, just the denominator. I don't care about the numerator. I don't care. Look at this, and I say, okay, what kind of factors do I have? Linear, linear, and they are distinct. That tells me right now, okay, that tells me that this guaranteed breaks into 2 fractions. How do I know it's 2? Because I have 2 distinct linear factors. That means that it's going to be 2 fractions. Not only that, I also know that the denominator of this fraction must be one of those factors, and the denominator of the other fraction must be the other factor. Okay, the method, I'm telling you what the method is, as opposed to writing it down like steps. I'm saying however many distinct linear factors determines how many fractions it breaks down to be, and each fraction has as its denominator each of those distinct linear factors. So had this broken down, let's just say we had a different problem. If this had 7 distinct linear factors, I would have 7 fractions, and each fraction would have each of the distinct linear factors, all right? What I don't know is the number that's up here, right? I don't know what it is. And I don't know what number's up here. Now, we do know because I made up the problem earlier, right? But right now, we don't know. So since I don't know, I'm gonna have to figure out what that is, right? And I have to figure out what that is. I have to figure out both of these. So I'm just gonna call this capital A and capital B. That's the standard we use for partial fraction decomposition. Could we what?
Like divide.
How do you mean?
What are the 2 linear factors?
Divide? I'm not sure what you mean by divide.
Yeah, just like 3x minus 1 divided by x minus 3.
Do this divide by that? How would you divide that though? Like how would you divide that? What do you mean?
I think
Oh, you mean like to make it go away so we could figure out what was here?
yeah.
Oh, if you could make that go away, but you're not going to be able to make it go away, right? Because these aren't exactly the same. But we're going to do something similar to it. We're going to do something kind of like that. All right, so do y'all see right now that we just need to figure out what A and B are? If we can figure out what A and B are, we're done. Okay? So how do we do it? Here's how we do it. I'm gonna rewrite it over here just because I have too much stuff written there. I'm gonna take 3x minus 1 over x minus 3 times x plus 1 equals a over x minus 3 plus b over x plus 1. Now, I'm going to clear the fractions. In other words, I'm going to multiply the left side of this equation by the LCD. And then I'm going to multiply this side of the equation by the LCD, like that. Now, you might be asking, why are you doing that? Well, just do it and you'll see why. When I do it here, what happens? Cancels out and you just get 3x minus 1. And then over here, what happens when you distribute, because you have to distribute, right? Here to here, the x minus 3's cancel, don't they? Right, because I'm doing a over x minus 3, but I'm multiplying by x minus 3 times x plus 1, right, when I do that. And then this goes away, and so you just have the a times the x plus 1. And then plus, now when you do this to here, what cancels this time? The x plus 1. So you're left with a b in front of what? X minus 3. Okay. Do y'all agree I could do that? Factor, two distinct linear factors. Okay, two different fractions. I don't know what a and b are. All right, multiply both sides by the common denominator, which is this. That clears all fractions out, and we get a new expression. I need to figure out what a and b are now. So the problem with figuring out what a and b are at this point is that I actually have 3 variables in one equation, right? It's impossible to figure out a unique answer if you have 3 unknowns in one equation. Right? Like if I just look at if you have 2 unknowns, right? That's one equation and 2 unknowns. There's an infinite number of answers to this, isn't there? So how are we going to figure out what a and b are if there's like an infinite number of things because we only have one equation? What we're going to do is we're going to be extremely clever, okay? We're going to be extremely clever. I'm going to do this. I'm going to say let x be equal to, and I'm going to pick, so I'm going to assign a value to x right now, but I'm going to be really, really clever about it. Right now I'm thinking I would like to solve for a. So in order to solve for a, what I'd like to do is eliminate this b from the equation completely. And to do that, I can just let x be 3. Do you all agree if I plug in 3 for x? 3 minus 3 is 0, and it would just kill this whole term off. So I'm going to let x be 3, and now I'm going to rewrite that equation, replacing all my x's with 3's. What's 3 times 3? I'll just write it. 3 times 3 minus 1 must equal a times 3 plus 1 plus b times 3 minus 3, right? I'm using this equation. Let me box this equation because I'm going to be using it again. So that's the kind of equation I'm working with. I let x be 3, and what do I get on the left side? 8. And then this is a times what? 4, so 4a. And then this over here is 0, right? So what's a? 2. Okay, I've got one of the 2 unknowns, right? Now I need to go figure out what b is. Yeah, so I'm going to start over. I'm going to go back to this equation. I'm going to say, hey, look, I'm trying to solve for b. Let's try and kill this off. How do you kill this? Let x be what? Negative 1. If x is negative 1, we get 3 times negative 1 minus 1 equals a times negative 1 plus 1 plus b times negative 1 minus 3. I think I'm off camera. All right, what is the left side? I think we get negative 4, right? Negative 4 equals, this goes away, and then we get negative 4b. And divide both sides by negative 4, and you get b is 1. So I figured out what a and b are, right? So here's what I can say. This expression right here can be rewritten as, you have to get them in the right order. Like you have to have A where A is, you can't switch those. So A was what? 2? Is 2 over x minus 3 plus, and then B over x, so 1 over x plus 1? Okay? And that is what I gave you when we started the problem, right? When I started this, I said, hey, recall from college algebra that if we start here, we can turn into this, right? And we were trying to go backwards, which we just did, using partial fraction decomposition. Now, why is this good? Because if you want to integrate this, it's the same as integrating this. And that is a constant over linear, and these are just super easy to do, right? That's the point, is that we start with something that we can't integrate easily. We use partial fraction decomposition to turn it into something we can integrate easily. All right, now this is just the beginning, all right? That was a very basic example. Look at those. Those are not as nice, right? So, try and decide. I'm not quite ready to go to that one yet. I'm going to make one up again. Let's do this. Let's try and integrate, or no, not integrate. Yeah, let's integrate. Let's do it. Okay, let's friggin' do it. Let's not hold back. Let's try. Oh, I forgot an X there. Oops. That wouldn't have been good. Now I'm making this problem up. I know it's going to work, but I know also we're going to get a lot of fractions. So just be aware. The numbers aren't going to be pretty like this. All right, so let's just make sure that we can't do this just right off the bat. It's not a quadratic, right? This is not a constant over a quadratic. So we can't use anything we talked about a little while ago. We can factor though, right? We can factor. Let's factor that denominator. Let's see what we get. What can we pull? An x? Now we have x squared minus 4x minus 5 on the bottom with that x. Now, you still can't do what we did before. Please do not try and split this into two integrals. You cannot do that, right? Because of multiplication. You cannot tell me that this is like 1 over x times 1 over this thing. I mean, you could tell me that's what it is, right? You could tell me that that's what it is, but you can't do these separately, right? You cannot, because there's multiplication in between. If it was addition, I'd agree with you, but it's multiplication. So you can't do that. Okay, well, this factors more, doesn't it? Okay, so we have integral 1 over x, what is that, minus 5 plus 1? dx. Well, wait a minute, hold on. I'm looking at this and I see 1, 2, 3 distinct linear factors, right? And so I should be able to do some partial fraction decomposition on this and get it to break up into like what, 3 different things that I should be able to handle, right? Okay, so I'm going to stop there and I'm going to do my partial fraction decomposition. Partial fraction decomposition. I'm stopping here and I'm looking at this. And I'm telling myself that because there are 1, 2, 3 distinct linear factors, I know it's going to be some number over the first distinct linear factor plus some number over the second distinct linear factor plus some number over the third distinct linear factor. So I'm going to have 3 things I need to solve for. Yeah, it's minus 5. I would get, yeah, I don't know, maybe it's blurry. Are you okay? It was minus. All right, it's good. Now what?
So
Multiply by the common denominator on both sides. When I multiply the left side by this, right, I'm going to get what on the left side? 1? Is that you? Who is that? Music? Is that them working outside? What is that? Is it outside? Okay. Is that it? Okay. It sounds like heavy music, like heavy metal music or something background. Just make sure it's not me. Do y'all see how we get 1 on the left? Right, we clear the fraction. What would this become? So, here, let me put it in here. I'm multiplying the left side by this, and then I'm multiplying the right side by this, right? When I multiply the right side, I have to distribute through. So this gets hit with x times x minus 5 times x plus 1. This one gets hit with x times x minus 5 times x plus 1. This one gets hit with x times x minus 5 times x plus 1, right? So you have to just see like what goes away, what stays. So the x's go. You're left with an a. What else? X minus 5, x plus 1. Okay, then b, what goes away here is the x minus 5. So you'll have the b, the x, and the x plus 1, right? And then here, the x plus 1 goes away. So you're left with the c, then the x, and the x minus 5, right? Damn thing's in my way. Any questions on that step? I have one equation, 3 things I'm looking for, and then a 4th variable x in there as well. But I have control over x. So I'm going to be clever. I'm going to try and start figuring out what I can let x be to solve for a, b, and c. So, whoa, hold on, that's not one. So the way I like to do it is I go after, like, let's go try and find a first, right? So you said what? 0, right? So why 0? If we're going to go try and get a first, right?
B or C, but A I'd do 5.
Okay, I'm not trying to kill a. I want to solve for a. So I want to make these two disappear.
So this is 0 for A.
So what would make this disappear and at the same time this disappear? If x is 0, right? Because they both have this x term in them. And if I let x be 0, it'll kill this, it'll kill this. Do you see that putting a 0 here and a 0 here does not kill this off? Okay? So I'm going to let x be 0. Now when I let x be 0, the left side of the equation stays as a 1. Right? That's still 1. And then a